I didn't mention this in my most recent video, but we are here in packet 9C. We're going to go ahead and get into example 8. We're going to try a different polynomial because we have a different function than in example 7. So what we want to notice first of all is we have an interval negative or 1.8 to 2.2, which means we're centered at 2, right in the middle of that interval. Okay, so if we're centered at 2, let me zoom in a little bit here, then that means we have to generate our values, our coefficients of our Taylor series. So we want third degree, so we're going to have to go, why did I do that? I meant to write f of x is equal to e to the x, and then let's make dot dot, f at 2 is equal to e squared. Okay, so then our first derivative at x of x is equal to also e to the x, and then f, so we can see the first derivative is also e squared, the second derivative is e to the x, so the second derivative at 2 is e squared, and so on and so on. We'll just write one more just to make it, just to round out what we're doing here, okay, because we need the first 3 derivatives because we want a third degree polynomial. Okay, so we can rewrite e to the x in terms of, it'd probably be helpful to write out what the Taylor series is, or the Taylor polynomial in this case, f of 2 plus f prime of 2 multiplied by x minus 2 squared over, I didn't mean to do that, that's not a squared, that's a 1. X minus 2, f prime, and then x minus 2 to the first power, plus f double prime, this is where we're going to get the squared, f double prime of 2 multiplied by x minus 2 to the second over 2 factorial, and then I'm going to have to squeeze this in here, plus the third derivative at 2 multiplied by x minus 2 to the third power over 3 factorial. Okay, so that's equal, so we have plus the remainder 3 of x. We're really concerned about the remainder 3 of x, so we really don't need to generate all these terms. I just wanted to re-emphasize that that's how we would do this, and the remainder 3 of x, and let's put that right here, the third degree remainder at x is equal to the fourth derivative at 2. Well, let's go ahead and fill that in now. Okay, we know that the fourth derivative is e to the x, so we know that the fourth derivative at 2 is e squared. E squared. So, and actually we don't want it at 2, we want the fourth derivative at z. So we're going to write the fourth derivative at z, okay, multiplied by x minus 2 to the fourth over 4 factorial. So let's think about this function, fourth derivative being e to the x. Okay, so if we think about the graph now we're not dealing with trig functions anymore, so we have to decide on what part of that interval is that derivative going to be at its greatest value. Okay, well, we know what the graph of e to the x looks like. That's the neat thing about doing these problems with an e to the x, because we know that e to the x looks like that. It's an increasing function, and so if we put 1.8 here and we put 2.2 there, it's not to scale or anything, but you get the idea. 1.8 here, e to the 1.8 is going to be right down here. Okay, e to the 2.2 is going to be way up here because e to the x is increasing. So we have a great upper bound for the fourth derivative of e to the x at some value in between 2 and 2.2 or between 1.8 and 2. So we're trying to look at this over an entire interval. Well, we can see, since it's an increasing function, that this guy right here, this is the most important part of this, that has a max value less than or equal to e to the 2.2. So we're going to just replace that guy right there with e to the 2.2 when we seek to find our error bound, our maximum error. So we say R3, and now we're going to, since we're centered at 2, we're going to look at the interval from 2 to 2.2. So we're going to let x be equal to 2.2 because that's going to be as far away from 2 as we're going to get, but also where we find that the fourth derivative is at its highest. Okay, so the absolute value of that is less than or equal to, again, here, absolute value, e to the 2.2. Multiply that by, we're going to replace x here with 2.2. Okay, x, 2.2, 2.2. And we can go ahead and put that in there, 2.2 minus 2. And we're going to raise that to the 4th power, all over 4 factorial. Well, I don't see any variables in here, and that's great because we don't have any. And we can just replace, we can put all this stuff into our calculator, and when we do that, I thought I had that here, but you should end up getting, if you want to pause and try this on your own, you may, you should end up getting 0.000602. That would be a wonderful number to get as our upper bound for our error when we use the third degree polynomial to approximate e to the x on that interval. And let's go ahead and zoom in on that part here. Okay, we've got, I said zoom in, but I backed out. 0.000602 represents, and again, I'm going to zoom in here a little bit and see if I can get this a little bit closer. Okay, so 0.000602 represents the maximum error when using this third degree polynomial to approximate e to the x on the interval from 1.8 to 2.2. Hope you enjoyed it.